Ever pondered why a spinning figure skater speeds up when they pull their arms in? Or perhaps why a moving car comes to a halt when it hits a wall? The answers to these intriguing questions lie in the fascinating world of physics, particularly in two essential concepts, momentum and angular momentum. Starting with momentum, it's a measure of an object's motion, calculated by multiplying the object's mass by its velocity. Imagine a car moving down a highway. The momentum of the car is determined by how massive the car is and how fast it's moving. Momentum is a vector quantity, meaning it not only has a size but also a direction. The direction of the momentum is the exact path the car is moving along. Now let's dive into a spin and talk about angular momentum. When an object is spinning or rotating like a pirouetting ballerina, it possesses angular momentum. Angular momentum is the rotational equivalent of momentum and is calculated as the product of the object's moment of inertia and its angular velocity. But what's the moment of inertia, you ask? It's a measure of how an object's mass is distributed around its axis of rotation. Just like momentum, angular momentum is also a vector quantity, and its direction is perpendicular to the plane of rotation. The real magic of momentum and angular momentum lies in their conservation laws. These laws state that the total momentum and angular momentum of a closed system remain constant unless an external force or torque acts upon it. In simpler terms, momentum and angular momentum can't be created or destroyed. They can only be transferred from one object to another. Let's take a practical look at these concepts. Consider a car driving down a road. It has momentum thanks to its mass and velocity. If it slams into a wall, the car's momentum is transferred to the wall, causing the wall to move. Similarly, a figure skater spinning on ice has angular momentum. By extending or retracting their arms, they can alter their moment of inertia, thus changing their angular velocity and the rate of spin, all while conserving their angular momentum. Lastly, a planet orbiting a star also possesses angular momentum, which remains conserved as it orbits the star. In conclusion, momentum and angular momentum are integral to understanding and predicting how objects move and interact. Whether it's a car on a highway, a spinning figure skater, or a planet orbiting a star. These principles govern everything from the smallest particles to the grandest celestial bodies, making them truly fundamental to our understanding of the universe.